Okay, welcome to the next session on Routh Hurwitz criterion. This links a little bit more to the control system analysis. Obviously, there's a previous video which looks at root locus plots. This is an alternative way to determine the stability of a system, and arguably one where you may not have the computer technology in front of you to actually analyze a system. So this is a quick way of doing it. It doesn't actually tell you how stable a system is because there's no graphical output. It'll just basically determine whether your system is stable or unstable, and we'll talk about how we can check that very shortly. What I'm going to do in this session, though, is verify the solutions against an actual computer output. So I will still plot the root locus plots just to emphasize that the solution we've got stands. So if the criterion output says our system's stable, I'll be able to show that to you. Or if it's unstable, again, show you why. Right. In this particular one, there's three distinct criteria to look at. There's a general scenario. There's a couple of special case scenarios where you may need to do something alternative when you do these calculations. Right. Starting off with the basic concept here. So it's still linking transfer functions and outputs, closed loop, open loop responses, etc. So in this particular instance, we've previously looked at how a root locus determines the stability of a system. So in the diagram below, we've got a generalized root locus diagram just to discuss. We said anything which had a negative real part. So you can see the real axis is in minus, is deemed to be stable. Anything that's right of the imaginary axis or the y-axis is unstable, and the imaginary axis itself is the point of neutral stability. Right. The tool today, the Routh-Hurwitz criterion, is used to identify whether a system is stable or unstable based on the roots of the characteristic equation. Doesn't plot anything. There's no graphical representation to prove it. It's just the physical output. Is it stable? Yes, it is. No, it's not. Right. Typical characteristic equation. For a closed loop is GH plus 1, and it'll be a series of S terms in the time domain. Typically for aircrafts, it will be like that. So we've got S power 4, 3, 2, 1, and a constant. Like this is what this represents. A naught being the constants, power 1 with the coefficients, power 2 with the coefficient, power 3, power 4. Quite often you might get numbers involved like that. Right. Emphasize the fact it's quarter function, typically in longitudinal sense. We have the few Gaussian short periods, which are power 2 terms each. In lateral directional, you have the Dutch roll, the spiral modes, and the roll modes are the four key ones out of that. Right. Jump into the actual plot itself and then explain how it works. So typically, this is a power 4 example. A represents the coefficients, S being an increase in power up to power 4. Right. We start off with descending powers on the left-hand side. We start filling in the first two rows based on the coefficient of the power 4, skip a term, the coefficient on the s squared term, skip a term, and we'll stick that value in. In the power 3 row, we start with the power 3 term. Then obviously we've already counted these next term, so we skip a term, do the power 1, and so on. So the concept of it is you're starting at the highest point, highest power, its coefficient, skip a term, and then you infill the other ones you haven't touched. Right, you can see in the cubic we've got that value, that one, we skip the term, there's nothing there, so it automatically fills in 0. Okay, the rest of the array fills in like this. We have a B term, a C term, and a D term for each corresponding row. And calculations for B, C, and D are through a series of matrices determinants. Right. With this being the power 4, if you sit and work out all the respective determinants, this one will calculate to be 0, this one calculate to 0, and so on. So these automatically infilled for power 4. Obviously, there's instances where maybe higher than the power 4, so this particular grid is not applicable. There's a couple of extra things to consider. Show you that very shortly. But in this particular one, B1, B2, we work out using the rows above. You can see B1 takes that block, A4, A2, A3, A1, and you always divide through by the bottom left of that determinant. And what you'll find is as you move across, so B2, this section stays the same. And instead of taking this block, we now take that section for the column. And the pattern continues. So if we add B3, it will be A4, A3 with whatever will be infilled here. So just right-hand column just constantly moves across. Right, obviously this grid can be as long or as big as you want. So it could be S to the power 10, 9, 8, 7, 6, so on. And you see the grid just gets bigger and bigger and bigger. There's more determinants to work out in each row, in each column. So it'll be B, C, D, E, F, G, and H, and so on. But there's just a continued pattern to the rules. So this is the idea I've just discussed in that when there's a B3 term, that bit stays the same. We're now over into the third column. Right, so obviously C1, C2, C2 continues. You should hopefully spot the pattern in the right-hand column, what's happening. Just moving across in each respective grid. So by the time you get to C, what happens is we've moved down into this block, C1, C2. Obviously, C2 takes that block with that one. So you need to work out all the B values in order to get the C values. It relies on the row above. Be a little bit more clearer in an example shortly. Right, what you can do, you don't necessarily have to do this, but when you've got numbers in the array, As long as there's a common factor involved, you can reduce it to a common number. So each of these values are divisible by 10. So you can divide by 10 in that row if you wish. You don't have to. It just makes the matrices determinants a little bit more easier to use and get the answers out. Doesn't affect the results, just makes your life a tiny bit easier. Right, example, show you how this works. Okay, right. Closed loop characteristic equation for the DC-8 aircraft is shown there. It says construct the Routh array, determine the routes in the positive unstable plane. So first off, it's a power 4 function. I'm going to produce that L-shaped grid. So S to 4, 3, 2, 1, 0. Right, values. You start with the S to the 4 value, which is 1. You skip and stay with the even powers now, so 1.219. Skip and then minus 0.015. Right, cubes starts with the SQ term, 1.326. Skip the even powers into the odd, so 1.096. And then we skip that, there's nothing there, so this one insert is 0. Right, we've got B1, B2, C1, D1 to work out. These automatically fill in 0. Right, B1, the minus determinant of A4, A2, all divided by the bottom left term gives A3. So take these numbers, that's going to be 1, 1.219, 1.326, 96, all divided by right. Just a quick recap for determinants if you're not sure or you can't quite remember. Top left multiplies the bottom right. Subtracts the top right, multiplying the bottom left. All divided by 1.326, and there's a minus sign outside there. So you should be able to stick that into your calculator. comes out 0.392. Right, so that is B1. So the first thing while I'm over here, I will stick in B1. Right, B2. First column stays the same. We then move across to A0 and 0. And still all over A3. Right, so it's 1, 3, 2, 6. No, minus 0.015 on top, 0 on the bottom of the other one, 1.326 to the divisor. Right. Minus 1 times 0. Minus 0.015 multiplies 1.326. All divided by 1.326. Hopefully you can see that equates to nothing. So we've got 1.326 on top, 1.326 on the bottom to cancel each other out effectively. So our solution is just going to be 0.015. Then with the signs, we've got a minus, that minus, and that minus. So 3 negatives gives us a negative overall. The minus 0.015 for that one. Right, in that goes. Right. We've now got B1 and B2. So into C1, it's exactly the same concept. So scribble that formula down. It starts taking the 2 rows above. So A3, A1. B1, B2. Negative B1. Right. Filling in the determinant, we've got minus. One 1.326. 1.096. 1.392. Minus 0.015. All divided by 0.392. Right, so minus, then in brackets, 1.326 times minus 0.015. Take away 1.096 with 0.392. All on the bottom is 0.392. Right, when you put that in the calculator, that should come out 1.146. Right, so that is C1. So that goes straight into our array. It just leaves us with D1 to work out. So B1, B2, C1, naught, all over C1. And you can see these two have moved up. In go C1, which we just worked out. And 0, all over 1.146. Back to 0.392. It's times by naught. There go it. No, minus 0.015 with 1.146. That's all divided by 1.146. So we get minus 0.015 out. It's the same as before. That equates to naught. Same on top as we have on the bottom. Minus, minus, minus. Right. Insert that into our array, which is over here. Right. To determine the actual question then, so the number of roots located in the positive unstable plane, all we're bothered about is the first column. Only bothered about those. And the signs only, not bothered about the values, just the signs. So that's 4, 3, 2, 1, and 0. We've got, right, that is positive. 1.326 is positive. S squared is positive. The s to the power 1 is also positive, but we've got a negative value for the power naught. Right, so when you go down from top, we've got no sign change. No sign change in that step. There's no sign change in that one. We've got 1 as we go into that one. Right, that indicates, so we've only got 1 full sign change from top to bottom. Means there's 1 unstable root for that particular function. Right, I'll verify that for you on MATLAB. As I say, the whole point of the Routh array is you don't have MATLAB in front of you, probably. But this is just to prove the points of the working out. Right, so just put system equals. Right, technical transfer function. We've got 1 for the top and the bottom. This is the coefficients of the question. So in the example, we had the power 4 function, which was 1. It says 1.326, the s cubed, 1.219 for the s squared, 1.096 for the s, minus 0.015 for the constant. Right. Just produce the root locus for that system because it's the easy way to verify what I'm doing. Agreed. Not that particularly matters in this instance, right? Quickly run that. There's our function, as you can see. Right, what we're bothered about is the crosses or the poles. You can see there's one there. This one, again, is not. Clearly stable, it's on the left-hand plane. Answer number 2 is clearly on the left-hand plane, along with number 3. Number 4 is only obvious when we zoom in here. Well, you can see if you zoom in, we have a negative pole, or in other words, one where its real value is positive. So there's one unstable root, which was picked up by the Routh array criterion. Right, we'll do that with the rest of them because it's going to get a little bit trickier now. Right, so that is the basic concept. We insert all the values, we look for the sign changes once we've got the values of B, C, D, and potentially E if it's a power 5. However, there's a couple of scenarios where that might not always happen. First one is if you've got a 0 in the first column. So for example, B1 might be 0, but B2 might still give you an output. So the problem is when we look for the sign change, it's not particularly obvious because 0 doesn't have a sign attached. The second one is when B1, for example, and B2 equate to 0. We have a problem where we try and work out what C is. Our solution is just going to keep on coming out as not. So 2 distinct issues to have a look at. Right, first one is when there is 0 in the first column, but the rest of that row will have numerical terms. We replace the 0 with the Greek letter epsilon. You complete it as normal, but it's a little bit awkward now. There's going to be an algebraic term involved. When we do the analysis at the ends, the value of E is positive, but infinitely small. Right, so it tends to 0, but it's not quite 0 is what that means. So E may very well be, just for example, something like that. So very, very clearly small number, but it's very, very, very just above 0, so it's positive. We need to bear that in mind when we do the final analysis. Right, so the example, and take this into the whiteboard. Right. Same as before, start off with the array. That's again power 4. Right, stick the values in. 1, 6, 7. And the cubed, 1, 6, and naught. B1, B2, C1, D1, all with the entries 0. Then off we go, right? I'm going to write the formula down for this one. They're all in the earlier example, but it follows the same suit. So B1 is the negative determinant of 1, 6, 1, 6, all divided by the bottom left. So that is 1 times 6, take away 6 times 1. You should see that very quickly equate to 0. So you've got 6, take away 6 equals 0. We need to put in our epsilon. B2 is 1, 7, 1, 0. Moving the second column into the next bit. Did all over 1. The 1 times 0. Take away 7 times 1. All over 1. That is positive 7. Insert now our values into the array. Right, very quickly with C1 and D1. Going to get a little bit awkward with the terms involved. Right, C1 says bottom of that one, so 1 and 6 for the top, with epsilon and 7 on the bottom. All divided by epsilon. Right. So 1 times 7. Take away 6 times epsilon. All of epsilon. That is 7. Take away 6 times epsilon. All over epsilon there. That is about as simple as it gets for that output. There's no simplification to be done. So C1, 7 minus 6 epsilon over epsilon. Probably needs a bit more space here. I think that should be positive. 7 plus 6 epsilon over... Oh. Positive, because I forgot to account for that bit there. So minus 7 plus that. So that's accounting for the fact that multiplies everything in. So, right. D1. Finish off. Right, so the bottom of C move up. So we've got epsilon and 7 for the top. On the bottom, we now have the awkward bit. We have minus 7 plus 6 epsilon. No epsilon. 0 for that. Right, what I'm going to do just to make life easy is make a substitution for the next bit here. So the horrible looking fraction, just for now, I'm going to label as X, just to help me deal with the simplification here. I'll substitute it back in at the end. Right, so we've got epsilon times naught. Take out at 7. But I've just labeled that bit as x for now. The same on the bottom. Right, and the reason I've done that is it's a little bit easier to see this. This bracket equates to 0. We've got minus, minus, negative, and negative. Turns up the answer to be positive. We've got 7x divided by x. So x divides that. So the output here is just going to be positive 7. Like that. Right, let's have a look. Dealing with the sign changes, remember, we're only interested in first column. Positive. Positive. Epsilon is a positive value that is just greater than 0, so that is positive. The 7 at the bottom's positive. It's just this s to the power 1 to think about. Right, just to emphasize the point, remember E or epsilon is just, you can use this to work it out really. You use that as its value. It's a very small number, just greater than naught. Right, that basically makes this output minimal. So it's going to be minus 7 plus a very, 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 very small number. So if adding a very small number to a negative value, it's going to be minus 6.999 and so on. Getting divided by that epsilon again. All that will do is make this value on top just increases the magnitude by a significant amount. So still going to be negative. Right. Sign changes then. We haven't got any to there, still positive. Haven't got any to that bit, so it's still positive. We've gone from positive to negative, so there's 1. Then we're back to positive, so there's a second one. Right, so this particular example has 2 sign changes. So we should have 2 unstable roots. See if we can very quickly plot this one in MATLAB. Right. Values in this question this time a little bit easier numerically. Yeah, 1, 1, 6, 6, and 7. Rest of the coding stays the same. We're just changing the outputs. So there we are. Nice and easy if we look at that bit. you can see, click on them, right? So the pole, negative, this pole, also negative. This one over here, the blue one, got a positive aspect. This one has a positive aspect. So 2 stable roots, 2 unstable roots. Right, something like this might very easily represent the longitudinal equations of motion for an aircraft. You might have the short periods, which you want to be stable. You might have the unstable fugoids because the e-pilot can correct it. Just obviously you want to keep the amplitude and frequency quite small. Right. The other example. So when you do the determinants and you end up with a couple of zeros in that row and you can't progress any further, we have to produce an auxiliary function that is based on the coefficients from the row above. So we take those values, we differentiate it, it will produce a new equation in which we substitute those coefficients in to the array and continue as normal. Again, this is going to be a little bit easier to see with an example. So produce an auxiliary function, differentiate, put those new values in as the array values to continue with. Right, so all values in the row where you're going to hit the set of zeros. Right, into the whiteboard again. Right, there's one extra thing I'm going to do with this, which I'll show you at the end. Starts off exactly the same as ever. Produce the array. It's a power 5 this time. Right, so we've got from the power 5, you've got 1, skip a term, 4, skip a term, 3. For the power 4, it starts as 2, skip a term to 8, skip a term to 6. Right, this time we've got B1, B2, 0. There's 2 in that one to work out. There's a D1 to work out, and this time there's an E1 because an extra row involved. The rest of them fill in a 0. Right, so starting with B1 and B2. One, 4, 2, 8 is the determinant all over 2. That's 1 times 8. Take away 4 times 2. All divided by 2. I'll quickly jot in B2 on them here. So we've got 1 and 2, 3 and 6 over 2. So 1 times 6, take away 3 times 2. all over 2. Now, hopefully you get a quick glance at these. 8 take away 8 is 0. 6 take away 6 is also 0. Obviously, that's the whole point of this particular example. Right, so in go 0 and 0. Now, it then says, because if you try and work C1 out, you'd have a set of zeros in one of the rows. If it used to be 0, take away 0, it'll eventually just constantly equating out to 0, so you can't progress. The statement said produce an auxiliary function from the row above. Right, notice I've circled the power outside as well. So the first coefficient is s to the power 4. So we've got s to the power 4, so 2s rather, to the power 4. When we inserted the values, we skipped a term. So each of these terms are a power missing. So this is now 8s squared. You skip a term for the 6, which is 6s to the power 0, or just 6. That equals 0. It then says in the PowerPoint that we've just been through the theory, it said differentiate the equation. So differentiating that, we get 8s cubed (16s) equals 0 because the constant disappears. Right, you can run with those values if you wish, 8 and 16. What I'm going to do is simplify this to make life a little bit easier. Both of these values are divisible by 8, so that is actually s cubed plus 2s. Right, notice this is now an s cubed term. We're going to slot into there. S cubed row. And the coefficients are 1 and 2. Right. The rest of it now just continues on as usual. So work out C1, C2, D1, E1. Quickly do them. So C1 is 2, 8, 1, 2 over 1. You know, 2 times 2, take away times 1. Comes out as 4. Right. Obviously, you can see the advantage of reducing the numbers down. Equations are a little bit easier to deal with rather than 8 and 16 hanging around, so you get larger numbers out. These are very easy to do mathematically in your heads. C2, we've got a 2 and a 1 moving across the row. We've now got 6 and 0 over 1. So that's 2 times 0. Take away 6 times 1. All over 1. Should come out as 6. Slot them into the C row so we can then work out what D is. That was 4 and 6. Right, D1. is 1, 2, 4, 6, all over 4. Right, so we've got 6, take away 8. Which is -2. We've got that negative there turned to +2. We're dividing it by 4, so that should come out as a half, 0.5. Very quickly leaves us with A1. So A1, you can see the bottom row is going to move up 4, 6, and from the row below that is now 0.5, 0, all divided by 0.5. 4 times 0, take away 6 times a half. 1 over half. Right, so that's 0. We've got 6 times a half, divided by a half is 6. Minus and the minus leaves that as +6. Right. Same as before, sign changes initially. We'll have a look at the sign changes. 1 is positive, 2 is positive. Our auxiliary function reduced to 1, which is positive. 4, half, and 6 are all positive. So if you look down this list, there is no sign changes. Right, no sign changes indicates none of the roots are unstable. Right, I will plot that on MATLAB again very shortly, but there's always a but. Right, the but. Do this in the correct color because we've done it in purple. Right. Because we had to go back and produce an auxiliary function that indicates something not quite as it seems. So what I'm going to do is go back to the auxiliary functions we've got up here. I'm going to take this auxiliary function and calculate the roots of it. Now I'll explain precisely why once we've got our answers right. Very awkward to do as it is. The first thing we need to do is make a substitution. pick any letter you want, but obviously it don't confuse it. So x is a nice one to make in this case, and then the substitution has to be s squared. So our equation now looks like this. Hopefully in that format, it looks a little bit more familiar. We now have a quadratic. So this one up here was quadratic in disguise, if you ever met them. Right. Dealing with this quadratic formula then, I'm going to stick it into the formula and get my answers out. So with the quadratic formula, if you can't quite remember, it says minus b plus minus the square root b squared take away 4ac. Got over to it. Right, we've got minus b, so that's minus 8 plus minus the square root of 64 minus 4ac, so that's 4 times 6 times 2. So 4 times 6 is 24. True. Times by 2. Four on the bottom. Just very quickly get the answers to this. Right, so x is either minus 1, so that's when you added the square root, minus 3. Right. If we go back up here, though, we've just said x is in fact s squared. So this first one should now actually read s squared is minus 1. This bottom one now reads s squared is in fact minus 3. We're going to square root this solution. Get two answers so we can get square root. So from theory, that says plus or minus j. Square root of minus 1 is often denoted as a j. This bottom one, same principle, square root of 3 minus 3 is in fact minus 1 times the square root of 3. Right, so you just seen there, minus 1 is in fact j. When you square root something, we get a plus and a minus. So there's our other value, right? Obviously, the square root of 3 doesn't mean much to anyone numerically. So just for the emphasis of what I'm about to do, we've got plus or minus j 1.73. Right. What does all of that mean then? So we went through the process, filled the array in, there's no sign changes, so there's definitely no unstable roots. What the auxiliary function tends to do is indicate that there are some mutually stable roots. What we've just worked out there are the solutions to all four of the neutrally stable. So in fact, of the 5 roots, I'll show you this in MATLAB again shortly. It's 5 roots because it's power 5. We find one of them is stable, 4 are neutrally stable, and the answer to those 4 is plus j minus j plus j of 1.732 minus j of 1.732. Notice there's no real number to these. There's no, if you do as a conjugate or treat as an x and y, there's no real aspect because on the plot it should be here, where the real component is in fact 0. Right. Into MATLAB one last time. Right, so the question this time says 1, 2, 4, 8, 3, 6. Just clear this. We run that now. Right, 1 stable root, you can clearly see it minus 2. The rest of them, (1.73i). Obviously, that's an astronomically low number. We just ignore. So 0 plus 1.73i. Got the negative version down here. This is symmetrical, remember? Same with these two. Because it's symmetry, we should have one a positive I and one negative I. So which you can see there. So the real components also very small, which we'll ignore. Plus I, negative I, or as we've done at J. That verifies the solution. So in this particular instance, when you get an auxiliary function, it indicates how many neutrally stable roots you will get. So it's a power 4 function. There should have been 4 neutrally stable roots out of this. Right. That does end the Routh Hurwitz session as well.